Thank you, and then welcome to the next session of double integrals and polar coordinates. So in the previous video, we looked at solving a problem which is given in slide 1. We realized that it will be difficult to solve in the given domain. That is because our limit of integration was a circle. I gave you the table of how to plot these values, and we ended up in a circular region. And at the end of the session, I said that if you have a circle, you use what we call the polar coordinate. How do we do that? And so that leads me to my next slide, which is on double integrals and polar coordinates. I'll skip the objectives here. I'll come to that later. So let's start with the polar coordinate. You realize that with the rectangular domain, our interest of our variables of interest was x and then y. That means we have a function of x and then y. And it implies our domain was dx dy. Now, in a circular domain, as if we are taking a piece of a circle like a pie or a pizza. In that case, the variables of interest is r and then theta. It means our function is f of r and then theta. The interesting thing is that our domain of integration becomes r dr d theta. So we know the difference. For rectangular, it is dx dy. For general regions, it is still dy dx, but for circle, I'm stressing on that. For circle, our dA is r dr d theta. Some will be like, how come we had this? When we get to the coordinate change of systems, we realize how r dr d theta came about. But for now, we take it in good faith. Okay. This r is called the radius of the circle. This theta is the angle of the circle. So radius is from a point 0, 0 to another point on the xy plane. Theta for a full rotation in degrees, it is 360 degrees. Its equivalent in radians, we all know it is 2 pi. If I have a half circle, in degrees, it is 180 degrees. Its equivalent is pi. If I have a quadrant, in degrees, it is 90 degrees. Its equivalent becomes pi on 2. So radius here becomes some 0 to A, some 0 to a point A, from 0 to a point A for all three structures. Okay. So having said that, you would like to know how to do this integration. So I've talked about slide 3, 4, and I'll move to the 5th slide. For the integrals and the rectangle, let me move straight here. It is always a double integral. So because I'm doing something different, let me use a different marker. It is always a double integral dx dr dy. And so if we have r dr d theta, it means that it is going to be a double integral r dr d theta. So that's what we see in equation 1 and equation 2. That is what it means. So in place of a double integral over the function f of xy dx dy, I'll have it in a polar as f of r theta r dr d theta. This is the difference. So someone will then ask, how do I know I have to move from polar? Do I always have to draw the domain? Do we always have to draw and see whether we have a full or a half? Oh, my half is not cool, but that is it all. It's just one sector of it. If you can draw, you draw. If you can't draw, there are things we look out for. Number 1 is that you check the integrand limit. If you see some expressions like a square root of a number minus x squared, or a square root of a number minus y squared, something should prompt you that it will be complicated doing my rectangular thing. I have to move to polar. The second thing to look out for is that, so it can be a negative lower limit. Then you know you're in polar. The second thing is that I have to look at my integrand. What I have under the integral sign, if is the expressions of this form, then I move to polar. So these are the things you look out for. If you can't draw, these are the things to look out for in any given question under double integrals. And so that leads us to our main question we're trying to solve. How do we find the solution to that? So I'll go back to my motivation, which was a circle. My last remark is that if you have the limit of a 0 to a positive side of that, it would always be a half circle or a semicircle. If you have it as negative that to another number, it would still be a half circle. If you have it as negative to the positive part, as we saw in our motivation, then you get a full circle. These are so obvious. So let's take our question again and try to evaluate it. I think it will be best to take. So the question was to solve negative 2 to 2, negative of 4 minus s squared, positive of 4 minus s squared, and then the integrand. We said, hey, this doesn't look so cool to solve in rectangular. So I see the remark here. I see this remark. I have this guy. So polar. I also see a combination of x squared and y squared. So polar. These are some of the things to check out for, which I've already done. And so let's continue. Before we can solve this, another thing we have to understand is that how do we convert from xy to the r theta? How do we convert from xy to r theta? This is what we do. There are some classifications. Always your x is given as r cos theta. The b, your y will be converted to r sine theta. Do not interchange them. X goes with the cos, y goes with the sine. And then, so what it is our r? R is given as the square root of s squared plus y squared. If I do a substitution, I have square root of r squared cos squared theta plus r squared sine squared theta. This gives me square root of r squared out cos squared theta plus sine squared theta. And you know from our trigonometry, cos squared theta plus sine squared theta is 1. And hence I simply have my root square of r as r. So indeed, this preamble is correct. And by algebra, I could also say that my x r squared becomes simply s squared plus y squared. That is from C. I could say that. Let's go back to the last definition. Now, theta is given as the tan inverse of y over x. These are things we look out for in converting from rectangular to polar. And so with this, I can quickly get my representation in polar for the question. I have to write that again. Anyway, so I have integral negative 2 to 2, negative 4, you would realize that for this double integral, my y is the inner. The y is -4 minus s squared to the positive side. Then my x is -2 to 2. We said this will give me a circle with a radius 0 to 2. The radius starts from a point of a center 0. So this is my R. And because it's a full circle, I'll have 360 degrees, which is 2 pi. What does this tell you? It means that your R from X is 0 to 2, and then your theta from Y is 0 to what? 2 pi. And so by substitution, and our dy dx, where do I take that? Our dy dx becomes r dr d theta. So I'm substituting 1, 2, and then 3 into the equation. So this is given as 0 to 2 pi, 0 to 2 for the radius s squared plus y squared plus 3 r dr d theta. You can simplify this further, sorry. And how do we do that? So I'll have this representation. Oh, okay. What do we see? S squared plus y squared. From our conversion here, we said that s squared plus y squared is equal to r squared. So by substitution, I'll have r squared plus 3 r dr d theta. And so I have 0 to 2 pi. By expanding, I have r cubed plus 3r dr d theta. As a final representation, you could tell that this is so easy, and then it is simple to evaluate this double integral other than the original problem. So I've been able to convert from, I did a conversion from -2 to 2. To 0 to 2 pi, 0 to 2, r cubed plus 3r dr d theta. Which one do you think is easier to solve? We've already made a motivation clear. And so I've been able to convert from Cartesian coordinate, a function of f of x here, to a function of r theta. This looks simpler to solve. I'm not sure of the answer we are going to get for this, but you are all good in solving double integral, so you should be able to evaluate this. And so in summary, what can we say in summary? You can always solve a circular region with a polar. I'm stressing on that. We move with the variables r theta, and then our dA becomes r dr d theta. We convert using these guys. Wherever you see x, you place these guys in it. And that is what you have to do. Again, also it says that if you have the limit of integration, having some square root of a minus any of the variables, you should know you are in polar, where the radius becomes 0 to that a, then theta becomes 0 to whatever you have, whether it's 2 pi, it is pi on 2, and any other region or degrees you can have. I will end here for the next thing. What we will look at next is how to evaluate. And okay, so I'll move to the objective as the next thing. There are two cases to do this evaluation. One is that when the polar coordinates are given. And the second case is that when you have to figure them out. So I'll say figure it out. This is our next session, and I hope the simple intuition has been understood. So see you in the next session for case 1 and case 2.